Okay, so let's look at one more example here, checking to see whether a series converges absolutely or conditionally. So here we have the alternating series minus 1 to the k over the square root of k to the 3/2 plus k. So we're going to test absolute convergence in a moment, but real quickly, I definitely can see that at the very least, as soon as I see this problem, I conclude, hey, this looks like it's converging, at least for the alternating series. This passes the alternating series test because if we did the limit of that stuff, as k goes to infinity, of 1 over the square root of k to the 3/2 plus k, that's going to be 1 over infinity, and that's going to be 0. So we have that alternating series at least is going to converge. There's only one other thing we have to be concerned with. Yes, our terms are positive, and does this thing always be non-increasing? Well, yeah, as the bottom gets bigger, as k gets bigger, the bottom gets bigger. Square root of stuff keeps getting bigger is going to keep getting bigger. And so divide by something that's bigger, the whole thing is going to be getting smaller. So the overall sequences of the terms inside are decreasing. So it checks off on the alternating series test. So we do know that the alternating converges. Now we turn to the question of what about absolute? Okay. And this one again just stood out to me immediately. I knew that the alternating, because I just saw I got 1 over stuff with variables raised to powers, and I immediately concluded, hey, it's definitely going to work for the alternating series. Will it now work for absolute convergence? So for absolute convergence now, we'd be looking at the sum of the absolute value of the stuff. That would just be that same series without the alternating sign there. Square root of k to the 3/2 plus k. This is a very ugly one to try and apply some of our tests to. Not looking forward to trying to do the root test on this or the ratio test. Also wouldn't even be looking forward to doing the integral test on this. And unfortunately, the divergence test doesn't let us reject it because we just said the limit of the underlying sequence there does go to 0. So all we have at our disposal is, at this point, the comparison test or the limit comparison test. So we're actually back to using that this time. So we're back to the limit comparison test just because of what it looks like. And so remember with the limit comparison test, we say, okay, as k gets really, really big, the only thing that's going to matter in that denominator is the largest power. Right? If k gets really, really big, this is just going to be the same as 1 over the square root of k to the 3/2. But that would be the same as 1 over k to the 3/4. Taking the square root would be the same as raising it to the 1/2 power. And so we have 1 over k to the 3/4. That is a p-series. It's less than 1. So because we have an exponent less than 1 in a p-series there, we know that series, the 1 over k to the 3/4, is going to diverge. Right? We know that series is going to diverge. So we suspect that our series will also diverge. But we can't just because it compares to one that diverges, we have to actually establish it. And we do that, remember, by taking the limit of our series divided by our comparison series. Okay. So let's do that. Limit, as k goes to infinity, of 1 over the square root of k to the 3/2 plus k all over 1 over k to the 3/4. So the 1 over the k to the 3/4 will jump up top. k to the 3/4 will jump up top. And we have a limit to work with here now. Now, this is an infinity over infinity limit. So you have the option in your back pocket of trying L'Hopital's rule. But in my experience, and we've seen some examples here, and I don't know what's going to happen here if we try L'Hopital's rule. But what I know is I've had some experience with these, and we've actually encountered these a couple times now. We did it back in, might have been 7.6. Let me just check and look for it real quick. Okay, it was actually back in 10.2 when we were looking at limits of sequences that we encountered this one here, k over square root of k squared plus 1. Right, and when we started investigating that with L'Hopital's rule, we started out with x over the square root of that stuff. And then once we simplified everything and cleaned it up, we ended up with the square root over 9x. And then if we'd have done L'Hopital's rule again, it actually would have flip-flopped and taken us backwards. So I don't know for sure what's going to happen with our problem. But because I have that in the back of my head, I think of that as, you know what, maybe trying to do L'Hopital's rule and take the derivative here might not be the best approach. So instead, with that history, I'm going to get inside the square root there. I'm going to get inside the square root. I'm going to do that by multiplying both top and bottom by 1 over the square root of you have to excuse me there, my mind just stopped working for a second. Sorry there, my mind just totally paused for a second. We would multiply by 1 over k to the 6/4. That way when we do square root, that would be the same as raising it to the 1/2, 6/4 to the 1/2. The 6 and the 4 would cancel. We'd be back to k to the 3/4 there. And same thing in the bottom. Divide by 1 over the square root of k to the 6/4. Of course, when this joins with the guy on top, they're just going to cancel out. And we're going to have the limit as k goes to infinity of 1. And in the bottom, that k to the 6/4 will simplify to be k to the 3/2. K to the 3/2 will cancel with the k to the 3/2. So we're going to have square root of 1. And then finally, we're going to have k over k to the 3/2 will be 1 over k to the 1/2. And now we can take this limit. This is just going to be 1 over the square root of 1 plus 0, which is just going to be 1. And so the limit is 1. And therefore, by our comparison test, since the limit is 1, remember what the comparison test said. It's been a little while now. But if the limit of the ratio approaches a number, then they either both converge or both diverge. And so therefore, we know that the absolute is going to diverge, just like its component p series friend, 1 over k to the 3/4. So we know that the absolute one is going to diverge. And so we already said earlier that the alternating one will converge. So the alternating one converged, the absolute one diverges. And so therefore we finish this off by saying that this one converges conditionally. Okay, our original sequence there converges conditionally. Okay, so our original series there, the alternating series of that stuff, converges conditionally. Okay, so this had to bring back our good old friend, the limit comparison, because none of our other tests would have been very fun to try to do with this. Wouldn't want to try and integrate it, right? I don't think it would be very fun to try and do ratios of that stuff. Just doesn't seem very fun. And it also doesn't seem very fun to try and do roots of that stuff. So none of those things are exciting. So therefore, we fall back to our limit comparison test.